Good day, everyone. It is nice over here for you and I because learning never ends and education is the key to an impactful life. My name is Anthony Nathaniel.
Good day everyone, my name is Anthony Nathaniel. I welcome you back to this channel, and today we'll be dealing with trigonometry, and it's going to be a very interesting video, so stick right to the end so that you can gain as much as possible from this video. Now today, for good reason, we're going to be starting with Pythagoras theorem, and Pythagoras theorem is at the foundation of trigonometry because it describes properties of a right angle triangle, which is also the main subject of trigonometric ratios. So now, in Pythagoras theorem, we have a right angle triangle, and this theorem states that the square on the hypotenuse is equal to the sum of the squares on the other two sides. So as you can see in this diagram, we have in the figure A, we have a right angle triangle, and the reason why we know it's a right angle triangle is that the angle ACB is a right angle. Now in figure 21.1, AB squared is equal to BC squared plus AC squared, or you can say C squared equals A squared plus B squared. Now that is one property of right angle triangles. Now in the second image, in the second colored image, you can see that when we stack the sides of three different squares, we'll get a right angle triangle. Now you can see that this triangle, these are squares, C squared, and we have A squared and we have B squared. So those are the right angled triangles that is formed from these three squares. Now notice also A square is C square minus B square, and B square is C square minus A square. So when we reorder Pythagoras theorem and make each of the sides the subjects, we can get any missing side. So in the second diagram, we have a geometric interpretation of Pythagoras' theorem. Next, let's deal with an example in Pythagoras' theorem. And here we have that in figure 21.12, if AC equals 12 centimeter, BC equals 5 centimeter, CD equals 11 centimeter, we are asked to find segment AD. Now in this diagram, you can see that ABC is a triangle. Triangle ABC has the side AB as Y, side BC as 5 centimeter, side AC as 12 centimeter. Then it also has side CD as 11, which were given to us in the question. Then the unknown sides are represented as side AB and side AD, which are Y and X respectively. Now continuing with the question, we have let AD be X centimeter and AB be Y centimeter, so which we've given them. Next we have that Y square equals 12 square plus 5 square. So as you can see, that is speaking from triangle ABC. Or rather, Y square equals 12 square minus 5 square. So that's 12 square is 144, 5 square is 25. So when we look for the difference, we have Y square equals 119. Now moving on to triangle ABD, we have X square equals Y square plus 16 square. So X square equals Y square, which we found it to be 119. So we plug that 119 into the equation and we get is equal to 119 plus 256. That's 375. So then therefore X will be the square root of 375. That's 19.4. So in this case, we have the length of the side AD as 19 centimeters to two significant figures. So you should notice that Y represents an intermediate length. When Y square was found to be 119, there was no need to find Y. So that is, since it was Y square that was needed in the subsequent working. Now let's get to the part where you all have been itching for, and that is trigonometric ratios. At the heart of trigonometry, we have these three ratios of the pair of sides of a right angle triangle, and we have this as the sine, cosine, and tangent of those sides. Now, the trigonometric ratios sine, cosine, and tangent are defined in terms of the hypotenuse, opposite, and adjacent sides of a right angle triangle as follows. So we have this right angle triangle. We are told that the hypotenuse, we have it as this side, and then we have the adjacent side below, and then we have the opposite side at the right. So we have that sine theta is equals to opposite over hypotenuse, cosine theta is equals to adjacent over hypotenuse, and then tangent theta is equals to opposite over adjacent. Now these are called the trigonometric ratios, and one thing you should know is that these ratios, they are three ratios. They are unique for a particular angle, but when we change the angle, they also change completely. Now I'll give an example in this question, and in this example we are told that to calculate the length of the sides marked A and B in the diagram. So as you can see, we have this triangle ABC, and side AC has a length of B, side BC has a length of A, side AB has a length of 5 centimeter. Then we have an angle of 35 degrees. Now anytime you see any question like this where you have an angle and a side, and you're asked to look for any other side in the right angle triangle, you make use of your trigonometric ratios, which are your sine, cosine, and tangent. Now the tan 35 equals, in general, tangent is equal to opposite over adjacent. So we are looking for the opposite of this angle 35, which is A. So our tan 35 will be A all over. Then the adjacent is the side not facing the angle, which is 5 centimeter. So tan 35 is A over 5. When we cross multiply, we have A is equals to 5 times tan 35. So plugging in our values from the trigonometric table, we have A as 3.501. So that is the length of the side A. Then when we're looking for the length of the side B, we'll make use of cosine ratio, which is adjacent over hypotenuse. So in this triangle, the adjacent to this angle is side AB, which is 5. Then the hypotenuse is side AC, which is B. So that means our cosine will be 5 over B. When we change the subject, make B the subject, we have B is equals to 5 over cos 35. And when we divide, we have 6.103. So the sides are 3.5 centimeter and 6.1 centimeter long. So over the side, you can see the working in logarithm. If you are looking for the working in logarithm, is also there. Now there's one thing that we can understand by adapting from trigonometric ratios, and that is angles of elevation and angles of depression. So in this diagram, we have that the angle of elevation E of the top of the tower from a point A below. Now this angle of elevation is the angle of turning from horizontal upwards. So, and the diagram also shows the angle of depression of the point B on the ground from point P, which is the angle of turning downwards. It's also known as angle of depression. Now, angle of elevation and angle of depression, there are two things you need to understand when you are applying trigonometry in real life. Now, let's solve an example on angles of elevation and depression. Now, we have this as example 4. From a window 10 meters above level ground, the angle of depression of an object on the ground is 25.4 degrees. Calculate the distance of the object from the foot of the building. Now in this case, note that the angle of depression is the angle between the horizontal and the line joining the window and the objects. Now continuing over from where we stopped, we have that this is the angle of depression in the diagram, which is from the dotted line to the hypotenuse of the triangle. So that angle between the dotted line and the hypotenuse is the angle of depression. Now you can see that this angle, there's an angle alternate to this angle. That is the angle in consideration. So that angle, when we look at the right, it is a Z angle, and so the angle below is also 25.4 because it is alternate. Then let's use tan tan tangent ratios. So now we have the tangent. First of all, we are looking for the distance of the object from the foot of the building. So let's call it D, distance D at the base. Now that angle, the angle opposite D, which is the lower angle in the right angle triangle, was the one that was alternate, and it is also 25.4. And the opposite of that angle is 10, and the adjacent is the base D. So because tangent is opposite of adjacent, we are going to use those same values of 10 over D. When we change the subject of the formula, we have D is equals to 10 over tan, so 25.4. When we plug in the values of tan 25.4 from the logarithm or trigonometric tables, we have our final answer as 21.06 from the reciprocal table. Or if we wanted to use the other angle, which is the complement of 25.4, we would be using tan 64.6 instead. So the reason is that when you in the right angle triangle, two of the angles sum up to 90. So if you are looking for the other angle, which is the complement, you just subtract from 90 and you get the complement of an angle. Now you can see that using the complement, you will still get the same answer. So at the end of the day, the object is 21 meters from the foot of the building. Next, let's talk about angles of 45 degree, 60 degree, 30 degree, 0 degree, and 90 degree. Now these angles I mentioned now, they are known as special angles because they, unlike other angles, can be represented as surds or fractions. Now they have the sign 45 is a special angle. As you can see in a 45 degree in right angle triangle, we have the when we have each of the opposite and adjacent sides as one unit, then by Pythagoras' theorem, we have the hypotenuse will be √2. And then when we look for the sine ratio, that would be 1 over √2 in a 45 degree right angle triangle. Then also the cosine ratio will be 1 over √2, which is equivalent to √2 over 2 when we rationalize the surd. Then for the tangent, we have the as 1 over 1, which is 1. So these are the sodical ratios of values of the trigonometric ratios at 45 degree. So let's continue with special angles. We have in this figure, we have this is a 30-60 degree right angle triangle because it has one of the complementary angles as 30 and the other as 60. Now in this special triangle, it is gotten by bisecting one angle of an equilateral triangle of side 2 units. Now in this case, when you can see that when we bisect the top angle, we have the bottom angles as 1 unit and 1 unit on either side of the bisection cut. Now in this left triangle, which is emboldened, the sine of the base complementary angle, which is 60 degree, the sine of that angle is √3 over 2 because it is opposite to hypotenuse. Then the cosine of that angle is 1 over 2 because it's adjacent to hypotenuse. Then we have the tangent of the angle is √3 over 1 because it is opposite of adjacent. So these are the corresponding ratios. Then also, if we're looking for the sine, cosine, and tangent of the complementary angle, which is 30 degree, we will still use the same method. Then for the 0 degrees, we have sine 0 is 0, cos 0 is 1, and tan 0 is 0. So these are default values, and we don't really need to prove that because they can also always be proved by your trigonometric ratios in the 4 quadrants. Then we also have that sine 90 is 1, cos 90 is 0, and tan 90 is undefined. Now folks, let's solve a question in that regard. So we are given that in this triangle, yeah, we are looking for this length of side RQ and length of side RS. Now RQ we are not given, and RS is also not given, but in the triangle QST, the sides are in the ratio 1:2:3 because this it is gotten by the bisection of an equilateral triangle from one of the angles, and you can see that is in accordance with the diagram we drew in the previous slide or picture. So then we have therefore side ST will be equals to half of side SQ. So that would be equals to half of 8, that's 4. Then side TQ will be equals to root 3 of root 3 times ST, that's 4 root 3. Then we also have in triangle QRT, the sides and the ratio of 1 ratio root 2, because this is a 45 degree 45 degree 90 degree right angled triangle. So then we have RQ will be equals to root 2 times TQ, which is root 2 times 4 root 3, that's 4 root 6. Also RS will be equals to, because RS will be the difference between RT and the ST, that's equals to TQ minus ST. That will be 4 root 3 minus 4. When we factorize 4 out, we will get 4 open brackets root 3 minus 1 close bracket centimeter. Now let's quickly go over one important aspect of trigonometry, and that is the sine rule. Now the sine rule, we will not derive it here because I've done that in another episode of this course, but the sine rule states that A over side A equals B over side B equals C over side C, or when you invert everything, you get sine A over A equals sine B over sine over B equals sine C over C. Now for any triangle ABC in which A, B and C are the angles of the triangle, and smaller case A, B and C are the lengths of the sides opposite these angles. So for the obtuse angled triangle, we have sine theta equals sine open bracket 180 minus theta. So this is the sine rule and is used for solving different questions. All you need to know is the side, one side and an angle opposite the side, and then you need another corresponding side or angle, so you can substitute your values and then look for any given side. Now it is not only the sine rule that is quite phenomenal in right angle triangles and trigonometry, we also have cosine rule. And this cosine rule it's used for solving triangles in which two sides and an included angle are given. So what you mean is that when you have two sides and an angle in between those two sides of cosine rule, so it's always used for special cases like this. So you can see that in this random triangle, this is not a right angle triangle. We have the a square equals b square plus c square minus 2ab cos a. Now you can see the triangle, and then we have b square equals a square plus c square minus 2ac cos b. C square equals a square plus b square minus 2ab cos c. So for this rule, you don't even need to memorize it or cram it into your head. All you need to do is just recognize the pattern. So you can see how it works. That on the left hand side we have the different term from the right hand side. So this formula are true for both acute and obtuse angles. In obtuse angles, cos theta equals minus cos open bracket 180 degree minus theta. So now I'll give an example related to that. So we have to find x in the figure. Now in this diagram, this is not an right angle triangle, but you can still use cosine rule because cosine rule works for all triangles. Next, we have that x square equals 8 square plus 5 square minus 2 times 8 times 5 times cos 46. So you can see that this is cosine rule, and the reason it works here is because we have two sides and an included angle. So we are looking for the opposite side, x. Now when we solve the equation, we have x equals root 33.42, which is equals to 5.781, and that is approximately 6 centimeter to one significant figure. So now let's deal with another example in this question. We are asked to find y in the figure. Now we have that y square equals 6 square plus 15 square minus 2 times 6 times 15 times cos 112, which is the included angle. When we solve that equation, we have y equals the square root of 328.4, which is 18.12, approximately 18.1 to 1 decimal place. Now you can study this question very well to see how the working is carried out, or you can work it out yourself to verify that the answer is correct.